This is the conservation of momentum template video. So this is going to make it as clear as possible how to set up the problems that you're about to try. So what you'll have to do is figure out which one of these three fits the problem that you're doing. Once you do that, just be careful on your signs for velocity and which numbers are plugging in where, and you should be okay. But if you have problems, as always, send me an email. All right, so let's go ahead and set these up. All right. And from yesterday, I'm not going to write it. I want to avoid confusion on this one note. But the idea here is that we're going to be applying the idea of conservation momentum right before and right after the collision. So split second before and split second after the collision. My pictures are going to be spaced out a little bit more than that just for clarity, but it's the split second before one thing hits the other and the split second after, so that there's no time for outside forces like friction with the ground to change the momentum of our system, the stuff that'll be in our picture. All right, so let's go ahead and start with a car crash. So let's go ahead and have a car going this way, and then car may be going this way. The directions here don't have to fit. The key is that in our before picture here, we have two objects, and the two cars hit, and let's say when they hit, they get tangled up, squished together, and they become a blob, like one object. So in the after picture, we'll have a mess. There's a wheel, maybe a wheel up here. I don't know how all that happened, but there we go. There's the after. And when you're doing these problems, you are required to have a before picture and an after picture. So make sure you have a before picture and after picture. And at most, you're going to have two objects in any one of these pictures for our actual ones that we're doing with the problems. So now what we're going to do, after I've drawn right before they hit and right after they hit, I'm going to go ahead and write that momentum before equals momentum after. If you prefer, you can use our maybe slightly more familiar notation of P naught equals P final, P initial equals P final, or P1 equals P2. But I'm going to go ahead and stay consistent with my before and after and write momentum before equals momentum after with shorthand for that. This is us saying the momentum is staying the same. If you don't write this line, you'd have to write a sentence saying, I'm about to apply the conservation momentum from right before the picture to right before the collision to right after the collision. Similar to the reason we write, there's lots of reasons, but this is similar to one of the reasons why we write F equals MA in summation of forces problems, is that we don't want to write all that. That's way quicker. This tells you what you're about to apply. So conservation of momentum, that's what this says. Okay? All right. Now, we're only going to be doing one-dimensional problems. In fact, this problem set is on these. Okay, so we're going to stick to 1D. So one way or the other, we're not going to have components and all that. So because of that, if you don't write all the subscripts on here, I'm okay with that. If we were doing this in class, I wouldn't even write them on the board right now, but I am going to put it in here in case somebody looks back at this OneNote and hasn't recently watched the video. So feel free to leave off some of these subscripts. As long as you get the answer right and you've got work that looks similar to this, you're perfectly fine. Okay? All right, so in the before picture, I have two objects. So to get this momentum before, I have to add up the momentum of this guy plus the momentum of this guy. And I'm going to call this car 1 and car 2, just to help with the notation here a little bit. So I'm going to have momentum of car 1 will be M1 V1. That's my momentum of car 1. Plus my momentum of car 2, M2 V2. So this is the mass of this car and the velocity, including the direction, the velocity of that car. This is the mass of car 2 and the velocity of car 2, or whatever those two objects are. Okay? And sometimes they'll be 0, and that's okay. If this was 0 times anything, you could just write plus 0, and that would be just fine. All right, equals. Now in the after picture, since the cars have squished together, they've clumped together, they've effectively become one object. So what do I have to do? Add the masses. So in the after picture of M1 plus M2, so this is me adding the two masses together, times the velocity in the after picture. So I'm just going to call that V, I'll call that V final. There we go. And that's our first possibility for one of these problems. So you'll draw a before and after picture, and if it goes from two objects where they're separate, distinct objects to one thing that's stuck together. Maybe there's a crash and they tangle up. Maybe somebody catches something. If they are stuck together in the after, but they were separate in the before, you'll do this. You'll draw a picture similar to this, and replace the cars with whatever it is. Write this line, and then substitute in. The number one mistake, if we were going to have a regular test day, the number one mistake would be that you would mess up a sign on the velocities. So if you get the problem wrong, obviously check your algebra, but then pay special attention to these V's. And typically we call right positive, and if you call right positive and you've got something going to the left, you'll have to make sure that you have a negative on that number when you substitute it in. All right, let's go ahead now. So that's the first template. Now let's go down to another one. Maybe we have a ball and another ball. So two objects in the before picture. And then maybe we're playing pool or something, and these two collide and the billiard balls go off in different directions. So maybe this happens in the after picture or something else. The key here is that we have two objects in the before. Maybe it's this kind of scenario. We have two objects in the before and two objects in the after. So whatever those two things are. Maybe it was two cars that hit and bounced off each other. Maybe it's a ball coming in and being hit off a baseball bat kind of thing. This is right before they hit. This is right after they hit. So two objects to two objects. I'm going to write my momentum before. Oops. Equals my momentum after. And then again, I'll call this object 1 and 2, 1 and 2. And this is a case where you don't need all these subscripts. If you just want to write like MV plus MV equals MV plus MV and have it lined up with your picture, because we're not getting any tougher problems, I'm perfectly fine with that. You can then just substitute in the correct values. Perfectly fine. I'm going to add all the notation just in case somebody looks back at this without having the video in front of them. So I'm going to have M1, V1, and this will be initial, plus M2, V2 initial, because this momentum before will be this MV plus this MV. That's the main idea here. Just figure out the mass times velocity of that guy, add it to the mass times velocity of that guy. So that's in the before. In the after, M1, V1 final, plus M2, V2 final. But again, you can drop all these subscripts if you want. Just this MV plus this MV equals this MV plus this MV. Remember, this MV is the momentum. If it makes you feel better, you could write, momentum 1 initial plus momentum 2 initial. You could do that kind of thing. Equals momentum 1 final plus momentum 2 final. If that helps you think about it, great. I'm going to go ahead and erase that now, but you could do an intermediate step if you want, if you're not comfortable with the momentum being MV right away. Okay? And then you plug and chug in there and solve for whatever you're looking for, whichever one of those typically velocities that you're trying to find. If this was the actual before picture and this object was going left, make sure that that's a negative. If this was the after picture and maybe you were given this velocity and it was going left, you'd have to make sure that was negative when you would apply that one. Okay? But there's other possibilities too. This could be just like not moving, and then this will be 0. Or maybe this isn't moving, and that's 0. Plug in what makes sense for the problem. But make sure you have a before and after picture, and if it's two objects in the before picture, right before the things hit, and it's two objects in the after picture, right after they hit, use this one. All right, now we've gone from 2 to 1 and 2 to 2. There's one possibility left, and you might not call this a collision, but that's okay. Let's say we've got Mario Ball, and this is the before. And Mario Ball has a stick of dynamite in him, okay, or a firecracker has been inserted into Mario Ball, and it explodes, okay? The nice thing about conservation momentum is right before that stick of dynamite or that firecracker goes off, and then right after, because those are internal forces, despite the fact that it's a mess, okay, that right before and right after he explodes, the momentum has to stay the same. Okay, there's nothing, nature can't finagle it at all. It has to stay the same. That linear momentum has to be conserved. So we're going to have him explode. So that's the before picture. And here will be the after picture. And the after picture will have, he is not happy. After picture Again, this is a split second after. One piece would have to fly one way, another piece would have to fly the other. Okay? So this is the momentum before equals the momentum after. Momentum before, I'm going to do the after first on this one. So in the after, okay, I had one object that now split into two. So I'm going to go ahead and call this like part 1 and part 2. So I'm going to have M1 V1 plus M2 V2. So the mass times the velocity of this part plus the mass times velocity of this part. That's the momentum after. You add up both of those parts. Now in the before picture, since they were stuck together, what do we have to do the masses? Similar to what we did up here, except in reverse, we're going to have to add the masses. So I'm going to have M1 plus M2, add together the masses, times that one velocity that we have in the before picture. So if you have a case where you have two objects that are connected, that might seem like they're two separate objects, but if they're connected, or if it's one object like this that's going to explode, but if they're stuck together somehow, that would mean you'd have one thing in the before picture, and then after whatever happens, if they fly apart and they're no longer attached to each other, that would be two objects. You would pick this one, and you would draw a picture similar to this, momentum before equals momentum after, and then this combined mass times the velocity of that. In this case, it would probably be 0, but it could be a number. It could be Mario Ball rolling along, and then he blows up, okay? Equals mv plus this mv. All right. And again, just watch out for your signs on your velocities. The number of the problems that you'll be doing will be in the, you should have already seen them in the tweet. Make sure you check your answers. If it doesn't work out, I would encourage you to double check your algebra, check your signs, and then you can always send your work to another student or send your work to me, and I can help you figure out where you went wrong if it's not working out. And I think there's one conceptual question at the very end about two soccer players hitting each other. All right, and that is it.